Hello and welcome to another video. In this problem we're going to be working on find an amount in an array. And so in this problem they tell you what a mountain array is, and basically a mountain array is an array of at least length 3, and then every element is either bigger or smaller than the one above it. So essentially if you draw out the elements it would be something like 1, 2, 3, have some peak, and then some drop down part. So the peak can't be the first or last element, so you can't have something like this, or like this, right? There has to be a left and a right side to the mountain, and that's pretty much it for that. And so given a mountain array, return the minimum index such that mountain array get index equals target. If such an index does not exist, return -1. You cannot access the array directly. You can only access it using a mountain array interface. And so the mountain array interface has get, which gives you the element at index k. So this would be just like you have an array and you're just getting an element at an index, and length, which gives you the length of the array. Submissions making more than 100 calls to mountain array get will be judged wrong. Also, any solutions that attempt to circumvent the judge will result in disqualification, whatever that means. So in this first example, let's make this a bit bigger and move it over here. So for this first array, we're looking for 3, and 3 is at index 2, so we want to return index 2. And also, so they do say that it can exist at multiple places, so index 2 to index 5, you want to return the smallest. And here we look for 3 and it's not there. So let's write down some things about a mountain array, right? Like, what do we know about a mountain array? 1, has a peak. All left elements are less than peak. And all right elements are less than peak as well. And there can be at most 2 copies of any number. And this is going to be important, right? So in a mountain array, you can't have more than 2 copies of a number because you have some peak. Well, let's just call this like some number, x. Then you can have like x minus something, like x minus 1, x minus 2, whatever you want. And this can be x minus whatever you want as well, right? X minus 3, x minus 4, and so on. But essentially, you can have the same element on both sides, but you can't have it repeating because every element has to be greater than or less than the one next to it, right? So you can have a copy on both sides, but you can only have 2 maximum. So essentially, to get, like, let's say we have this mountain, and then an element can be, where can it be? It can be a peak. It can be here. It can be here. Or it can be both of these. It can't be a peak in both of these because there's only one peak, right? Peak's greater than the rest. So our strategy is going to be as follows. We're going to find this peak. So find peak. Then check for target on the left. Then check for target on the right. And that's because we want to check the left first, because if it's on both the left and the right, we want to return the minimum index. If it's on both and we find on the left, we're done, right? Like we have a 3 here and a 3 here. We can just look at the left, find the 3, and then we're done. But we want to make sure to only use 100 API calls. So I will say this problem is more of like a medium problem, just a little bit lengthy. So it's interactive, and this is kind of remind you, like let's say you have API calls and you have like 100 API calls per day. Some of the strategies, I guess, like that you would use to make sure you don't have to pay for API calls, something like that. So we have to use 100 API calls, and also, by the way, the length of this array is something like 10 to the 4th. So if I actually did like a log of this just to figure out like, okay, well, if I do a binary search of this, how many API calls would I take? So I think 10 to the 4th is roughly, a log of 10 to the 4th is roughly like 14 or so. So you can actually make 3 API calls per index you find, and that would be like 40, so that would be fine. So essentially you could do 3 searches, but if you didn't do any caching at all, and you did like a bunch of API calls, like let's say you did 3 API calls for every index, then I think you'd be a little bit over. But our strategy is going to be 3 API calls maximum to find the peak at every index, which is going to be like roughly 14 times 3, which is like 42, roughly. And then we're going to check the left and the right, and maximum we only needed 1 API call there for each, so that's going to be like plus 14, plus 14. So actually this does pass without caching at all, and then you're going to get like a super space, you're going to get like 100% or close to it space efficient solution, but it runs a little bit slower, and I'm not sure why that is. I think maybe like the API calls might take some time or something, I'm not sure. But essentially, we're going to do this with caching, and in a real API call, you're probably going to want to have caching, right? Because you don't want to like spam an API call for the same information multiple times if those are valuable to you. So we're going to kind of demonstrate that, but you can, this does pass with zero caching whatsoever. But actually, it's more like a medium problem. Let's kind of go over our strategy, right? So we're going to find our peak. So to find our peak, let's think of our strategy. We're going to be at some index, right? Like, we're going to be at some index. So let's just say we have an array, and it's going to be a mountain array, and we'll talk about like what possibilities you can have. So let's just say we have like a really simple one. I don't think it really matters. 6, and then we have like going down here. And let's kind of talk about the possibilities we can run into. So one possibility, and now the other thing is we know that like we don't need to look for this number and this number in our left and our right. We're gonna do a binary search, but we don't need to like include these two because these can't be a peak, right? A peak can't be the last or first element. So we're gonna start here and here for the binary search, and essentially let's look at like I'm actually just gonna draw a little line under them to represent these are our bounds. So let's just look at a couple different like scenarios. So let's say we are at the left side, but it's not like the peak. So here we need one API call, right? So let's write down one API call. So let's look at our scenarios. A, we are on the ascent, let's call that. We need one API call to get the value, right? So whatever pivot we pick, we need one API call. Then we need one more API call, right? One more API call to figure out that we are on ascent, let's say. So for example, what you want to do is you want to just check if your element is actually less than the value you're looking for, right? Or like something like that, essentially. You want to try to minimize your API calls, right? So we could say, so one API call we could say is like, we can just check for the left side being less than the value. And what's that going to do for us? So let's say we're at this here. We can have one more API call to check if the left is less than the value. And so let's write that down. More API call to figure out if left is less than value. And then basically, if it's true, then this can possibly be our peak. So if it's true, then this can be our peak, right? And technically, I don't even think you have to minimize API calls. I think literally, honestly, I did it to minimize API calls, but to keep it simple, you can literally just get, API call this and both elements, right? You don't even need to minimize this third API call. So I guess I'm just going to explain it that way, but then my code will try to minimize the third one. But yeah, essentially, if you did want to minimize the third one, you want to see if the left is less than your value. And if it is, then this might be a peak, right? It's possible. So then you have to get also the right call. So maximum 3. But if the left is greater than our value, then we're guaranteed to be on the descent. So if it's true, we need one more API call to check for peak. False, we are on descent. So just think about like how you would get, how you would figure out like if it's a mountain array with minimum checks, right? So this would be 3 checks worst, or 3 API calls worst case, best case 2 API calls. So that's one case, right? Where we are on the ascent. And then in this case, what would happen is we would need 3 API calls because we would check the left, our number is greater than the left, and then we'd also need to check the right. And then we check the right and we realize the right is greater than our number. So then we realize we're on the ascent. And we can just get rid of like if you're doing hard problems, I'd assume you know how to do basic binary search and what to get rid of, right? So we can just get rid of like this section, and then we can keep checking this section for our peak. So that's one case, and let's actually leave that there. Now the other case is, let's say we are on the peak. So on the peak, we would compare to the left, same kind of thing, right? We'd get the value, get the left, and then we'd say, okay, our value is greater. Then we're going to have to do one more API call, check the right, and then we'd say our value is greater. Okay, perfect. Now, before returning this, we can check if we are the target, right? So if we are the target here, we can return. But we can't return in all these other ones because we might not be on the, let's say we just are here and we are the target, but there's also a 4 here. The only place you can return right away is the peak. So let's get rid of that. Okay, so that's the other case. It's like if we're at the peak, we just do 3 API calls, we figure it out. Okay, now if we're on this side, if we're on the descent, we're going to do the left API call, and then we're going to say, okay, well, the left is bigger than our value, so then we know we're on the descent just from that one API call. We don't need to check the right, right? If the left is bigger than our value, then we know we're on the descent. And then we know we can check the left side of that. So that's pretty much it. Like, you're just going to like have API calls, maximum 3 per index. Like I said, I think this ends up being like 40 API calls or so. Okay, now that we get a peak, so now that we have a peak, what do we do next? So let's copy this down maybe. Just actually bring it down here. We have a peak. And we know exactly where it is. We have the index, we have the value, right? And you want to also, like, every time you get the value. So the other thing we are going to do is every time we make an API call, we're going to cache the API calls to minimize our API calls. But like I said, this isn't necessary for the solution to work, so you don't have to do it. Okay. So now that we have a peak, then we're going to, check the left side. And we know exactly the indices, right? Because we have our peak index. So we can just check this part for the value. And then this is just a strictly increasing array, right? We're going to check every value below the peak. So check the left side for the target. Only one API call here. Because, like, let's say our target is like 5. And we get 3. Well, we know this left side is strictly increasing, right? So then we know where to go just from getting the value. Like, we're either going to get 5, in which case we can return, or we get a value less than 5, which means we have to go to the right, or we get a value greater than 5, which means we have to go to the left. So only one API call here. Then, if we don't find it in the left, so if we did find the left, we return, right? So I guess we can write if found, return, because that's going to be the guaranteed minimal index, because like I said, there can only be 2 copies of every number, one on the left and one on the right. So if you found it on the left, you don't care about the right. The left is a smaller index. Then 2, same thing for the right. Check the right side for the target. Only one API call as well. Because, once again, if your number is 5, let's say we're at here, we know it's strictly decreasing. So if we know we're at 3, we need to check the left. If we know if we're at bigger, let's say like our number wasn't 5, let's say it was like 1, and we're over here, then we know like, okay, well, it's decreasing, we're bigger, so we have to go right. Right? Just simple binary search stuff. So that's pretty much it. And yeah, like I said, we're going to be caching as well. So because we're going to be caching, we're going to save some API calls, but totally not necessary to solve this problem. But you would want to have caching in a real, like I said, imagine you had a free API, you're going to want to save API calls, right, to not call the same index multiple times. And yeah, that's pretty much it. So it's just going to be a lot of code and pretty simple. You get a peak, you check the ascent, check the descent, and that's it. Okay, so let's code that up. So we want to get the length just so like we could figure out what the binary search bounds are. So we can call that m, and then we're going to call this mountain array length is the function here. So we're going to get that. Now we're going to have our left and right for the binary search. It's going to start at 1 and at -2 because remember the last 2 indices, like the first and the last index can't be the peak. Then we're going to have the visited cache as well. So we're going to have a helper function, and it's going to be called getValue. It's going to take an index. And what it's going to do is basically just check, have we seen this before, right? So if we've seen it before, we're going to return it. So what we're going to do here is we're going to say if index is in visited, and we're going to use this a bunch, so that's why we're going to say if it's here, let's just return visited index. Otherwise, let's get that value. So value equals mountain array. Let's make our API call, get index. Let's cache it. And return it. Okay, so our first binary search is just going to be to find the peak. So we're going to say while left is less than r. We are going to get the pivot. As usual, trying to have my variables in as few characters as possible. So what we need to do, like I said, is we need to get, at minimum, we need to get the value and we need to get the left. So value is going to be get value at pivot. Left, the left side of that value is going to be get value at pivot -1. Now we're going to say if left is less than val, then we need to get the right. Otherwise, we don't need it because we know we're on the descent, right? So if we're on the ascent, we can be at the peak, or we can be on the ascent, so we need to get the right. So if left is less than val, let's get the right. Key +1. Let's get some more space here. get the right. And then let's make sure, so if value is greater than right as well, that means it's greater than both. That's the peak. So we're going to set the index there. And then if value equals target, let's return the result right away, because we're not going to save the value. We're just going to save the result. So if we found the peak, let's just break here. We don't need to do anything else. So otherwise, so this is the case where if our value is greater than the left, but it's less than the right, that means we're on the ascent, right? So if we're on the ascent, we need to go right. So let's go right. And then otherwise here, if our value is less than left, then we're on the descent. So we need to go right, or we need to go left, right? So let's go left. So now we have our result. Like I said, a lot of code. Now we have our result index. Now what I'm going to do is I'm going to make a helper function to do the ascent and the descent, because it's basically the same code with like a few lines of code different. So I'm just going to make a helper function here. Don't have to do it. You can just make it 2 more binary searches if you want. But yeah. So def search, it's going to take a left and a right and an ascending, whether for ascending or not. So we're going to do the same thing while left is less than right. Here, we're going to say, I mean, we can probably like copy most of this, change some of it. Let's move this over. Okay, so value is the same, but we don't need the left or the right. I guess we can get rid of this. So essentially, I don't know if this is tabbed right. So essentially, we just need the value. We don't need the left or the right here, because we know if we're ascending or not. So if value equals target, let's just return here, right? So let's return the pivot. Now we have to check for a bunch of things, essentially. So if value is less than target, we have to check if we're ascending or descending. So if we're ascending, that means if value is less than target and we're ascending, we need to go right, right? So we're going to say left equals pivot plus 1. But if value is less than target and we're descending, then we need to go left. So these are just basically the opposite. So right equals pivot minus 1. And then we have our else case where it's literally just the opposite again, right? So if ascending, we're going to do the opposite of what we did the last time. So r equals p minus 1, else left equals p plus 1. So we have our helper function. Now all we have to do is call it twice. So we can say climb equals search. And we're going to start the left side, right? So we're going to do 0. We're going to do result minus 1. That's going to be our like left and right. And we're going to say true because we are on the ascent. And if it's not, I think I actually forgot to return. Yeah, I did. So we need to return -1 as a default here, meaning like we didn't find anything, let's just return -1. So if climb does not equal -1, then we have a value, so let's just return that. Otherwise, we can just return search, and I think we want to return -1 as a default if we didn't find anything. So now we want to check the right side, so that's going to be res plus 1 to the length to the end of the mountain, which is m minus 1, and where m is the length, and we are not climbing, we're on the descent. So it should be a lot of code, but very repetitive. Let's see. So val equals mountain array, get index. We have a problem here. Probably, IDX. There we go. Anything else? I have an infinite loop? I think we do. Nope, apparently it worked. Or did it have an infinite loop? Infinite loop, okay. So a lot of debugging, I guess. Let's see if we get like part of this to work, and then we can do the rest. So let's say we try to do the first part, just return 0 or something, see if it's in the first part of the last part, and let's also get out of this. Start debugging like this. So it looks like it's in the first part. Yeah, it looks like it's in the first part, so let's fix the first part, yeah. Okay, so let's actually full screen again and fix the first part. Let's double check here. So this is fine, this is fine. Val is not an array, this is fine. We probably just like did the same thing twice or something. So val left equals get value, we get the left. If left is less than value, right equals get value plus 1. Value is fine, this is fine. Value equals target return res result. Oh, right. So this is not P plus, this is L. There we go. And looks like we have an error. Oh, it's because we commented out our stuff, right? So, okay. Let's do this, and let's get rid of that return 0. There we go. Okay, and you can see this one's pretty efficient. So let's go through the time and space. I mean, it should be reasonably straightforward, but so essentially we do three binary searches, right? One to find the middle, so it's log n, and then another log n, and another. So it'd be the first one's log n, second one's log n over 2, which is log n, and then the third one's log n over 2 as well. So basically it comes down to log n. And for the space, so we are caching, but we're not checking every element, right? We are only checking log n elements again. So it's log n. But yeah, you can actually completely get rid of this caching thing. And then when you run this, so I don't know how I had this like 98%, but essentially what would happen with no caching is you'd have like 100% space and it would still pass. So totally fine doing it that way. But yeah, that's going to be all for this one. So definitely a nice break from all the hard problems. It's been crazy, actually. I think we've had like 5 or 6 hard problems in this month and probably like none in the month before. So we'll see what happens next time. But yeah, this one's not too bad. So if you did like this video, please like it and please subscribe to our channel. And I'll see you in the next one. Thanks for watching.